Thank you very much. The genesis of this talk really goes back to spending time with my parents over Easter this year. Now, I know most of you are probably a lot like me and quite enjoy writing code, especially when it comes to choices that, or actually talking to one's family. So rather than being social, I decided that since I had my laptop, I might as well use the 4 days to actually write some code. And since I know a little bit about serialization in Corda, and I kind of have a thing for C++, combining the two might have been a good thing. So today, we're going to look at 3 things. Firstly, we're going to look at how serialized blobs in Corda are stored. Then we're going to use that knowledge to think how we could actually start writing a serializer outside of the JVM. Finally, we're going to take a look at a C++ project that actually starts to do this. Now, before we do that, we're going to dig into what is serialization. Because I know for a fact we've got an awful number of people here who signed up for both DevDay and BizDay, and they may be regretting their life choices by coming to this talk. So serialization is a very simply just the process of transforming data objects into a form we can do something with. So let's take a very simple example. Here we've got a class, it's got some properties, we've got an instantiated instance of it, and we serialize it. So we end up with a collection of bytes we can do something with. We can send it over a network, very much like the Corda flow framework. We can write it to disk, or we can put it into a database, very much like all of the states in your vault are inherently serialized blobs. So how does Corda serialization work? Well, to understand that, rather than deal with how you write it, how you read it, let's actually just dig into the data format. What is in my vault? Well, we have a blob. A blob, if we look at it, is a header and some data. That header is very simply just an 8-byte chunk. First 5 bytes spell out Corda. Next, we have a version string. So we have Corda version 1. Corda is going wire stable in around 3.3, if everyone remembers way back to Corda 3. And the final byte, well, we're just going to ignore that, but that's an AMQP section ID. But for all intents and purposes, we're just going to pretend it's 0 for the rest of this talk. Corda is wire stable. We use an AMQP format. How do we actually encode that AMQP data, though? Well, we use something called Cupid Proton. It's an Apache library. It is designed to make interacting with the AMQP ecosystem really, really trivial. And by looking at this, it's got documentation for all sorts of things. Obviously Java, which is what we leverage. But for my purposes, awesome, we've got some C++ code. In fact, there's almost more C++ done than there is Java. But for anyone thinking, well, I like C#, I like Python, well, we have a C API. We can embed this in any language we want. So what is Proton encoding? Well, Proton encodes data as an acyclic graph of nodes. Nodes have parents, they can have children, they can have siblings, and so on and so forth. Nodes have types, this is how we distinguish the data in a tree. They can be primitive, they can be floats, longs, doubles, strings. They can be containers, associate lists, maps, arrays. Finally, most importantly, they can be described types. Now, a described type is basically how we give meaning to sections of this tree when we only have primitive concepts to describe them. Now, described types have 2 children. Our first child is a 64-bit integer that represents this node. Now, the top 32 bytes are just a vendor ID, and that's unique across the AMQP ecosystem. So Corda has a unique vendor ID in that ecosystem. And the bottom 32 bits are literally just an identifier. So for those interested, this is Corda's vendor ID. It was registered by Mike Hearn. You can look it up on the AMQP spec site, and it will just reference R3. Now here are the described types that we care about. This is how we give meaning to what's written to disk. Again, quite a long list, and for the purposes of this talk, we're only going to look at the top 5. Envelopes, schemas, object, fields, and composite types. And for those interested and want a sneak preview of some C++ code, this is our descriptor registry in the implementation we currently have. Now, the second chart of a described type is a description of what is being described. And we're going to get into that in a little bit. So let's have a look at an example of Proton encoding. Well, we have a list of lists of lists. But more specifically, how would we store this list in a Proton structure? We have values 1 and 2, and goodbye, cruel world, because it's a hard life. So we know we have a list. So we have a list of lists. In this case, we know we want to store 2 lists. So the first node has a child, and that child has a sibling. And then we put the data into it. So you can see how we can mix data types to just very simply store data. So going back inside our blob, we know we have a header, and we know we have Cupid Proton encoded information. But what type of information? Well, going back to our described types, we have what we call an envelope, and that's where we stuff everything inside. What's inside the envelope? Well, we have a payload, what the actual data is. We have a schema that describes the data, and we have the transform information. But, again, for simplicity, we're going to gloss over the ongoing evolution of types and the transformations that you can apply to them. So again, looking back, the schema exists in our list of described types. We will keep coming back to this list to understand the data as it's written. What's in the payload? Well, it's AMQP, Cupid encoded, but again, it is literally the concrete values that made up that data. And the schema is a description of that data. That's how we store things on disk. That's how things get transmitted over the web. Let's look at how we could then use this information to build something outside of the JVM. To do that, let's look at what we do in Java, or in our case Kotlin, and work out why we can't leverage that. So inside the payload, i.e. the actual data, we find an object. Underneath that, we find a symbol. If we actually read the value, what we have is a hash. That hash is a fingerprint. That fingerprint uniquely identifies classes on the class path. If you change the class, it will change the fingerprint. If you evolve the class, it will change the fingerprint. This is very important in Corda and the way it works and how we have wire stability. So if in our Java implementation, on receiving a Corda packet, the first thing we do is go and look inside a factory, because we want to serialize it that it's going to understand this data. But if we don't find one, well, we need to build one. And the first thing we have to do is decode this fingerprint. Well, we know we can go and look in our schema, which quite simply will tell us, well, that's net.corda.example. So now we know the class, we can go to a class loader. What can the class loader give us? Well, it can give us the definition of a class. Now, what can we do with the definition of a class? We can build some instructions. We can work out how, based on the type information we have, how to then read it off of disk. So applying that, we can now understand how we wrote it. Now, it's important to realize we're not going to talk about the schema again for a little while. We enter the thing following our list of instructions. So we move into the blob, and we initialize a stack. We consume the first value and move on, put it into the stack. We consume the second. Now we exit. Now we move on to the create step. Well, we dug inside the class loader, so we know how to construct the object. We can find a pointer to its constructor. We've got values to pass into that method, so we just end up with a heap object. Great, we've decoded this live object. So can anyone see what the problem with this is? That's right. If we're not running in a VM language, we have absolutely no runtime reflection. So we cannot do dynamic fingerprinting of types. If we don't have any access to the Java type system, then the fingerprint's going to be very difficult to look at. It's almost certainly the fingerprints are going to be very hard to then match up, as Java string is very different from a C++ string, very different from a Python string. Finally, we cannot do runtime analysis. We cannot link as a constructor method to some abstract class. We would have to do this at compile time. So what's going to be our solution? Well, we addressed it a little bit earlier. We have a schema. We have a complete description of all the types in the payload. The fact Corda, Java implementation doesn't need to use it, apart from revolving, but we're not talking about that in this presentation, then why won't we just leverage that? So what's in the schema? Well, we can use it to understand the payload. If we can understand the payload, we can create some serializers, just as we did previously. We can then generate classes from our Java types that are constructible from deserializable blobs. Finally, we can then write a schema generator to generate native classes that are fingerprintable that we can then send into the Java side. However, I know everyone is thinking, that is an awful lot of work. And trust me, it is, because I started doing this and I am still hacking away. So what are we going to do? Let's go back to step one, using the schema to understand the payload, because that's a small chunk we can get into. So what do we mean by doing this? Well, at some point, we had a class inner and outer, and we created an instance of it, and we serialized it, and we wrote those bytes to disk. So now let's pretend We completely lost that code. We just have some bytes. What we want to be able to do is print out a meaningful representation of it to our console. What other reasons could we have for doing this? Well, we're going to gain some familiarity with Proton. If you're going to work with Corda schemas, if you're going to work with Corda blobs, then getting some familiarity with Qubit Proton is super important. We're going to gain familiarity with the Corda schema. How do we represent information? How do the transforms get applied? We don't have to write a class synthesizer. We don't have to write a cross compiler. Fun though that is, quite hard. Finally, we might have a slightly useful tool we can work with. So let's have a look inside the schema. And going back to our list of described types, the things we haven't looked at now are objects, fields, and composite types. And again, our previous example, we had two classes, inner and outer. But in the schema, we'll have three instances of that. Because we know we have to describe the inner class, we have to describe outer, but we also have to describe the list of inner, because that impacts how we wrote them, and we have to be able to work out how to decode it. So our schema is a described type. We have a reference to the schema, and that's a list. The list is the description of the type. And the schema is described by a list of its own. In that list, well, we had the three types. And this is where I told a bit of a lie earlier, because you may notice that we have a sixth type, restricted. List container objects are very, very different from composite types, and composite types are very simply just types made up of other types. But we're going to gloss over that and just look at the inner class. So what describes a composite type? Well, they have names, net.corda.inner. They have a label. Let's give some metadata to the class. Now, the next one is interesting. We have another described type, and this is our object reference. And those are paying attention will notice we had this repeated pattern over and over again in our tree. And again, as I said, described types give meaning to the encoded information. We have a schema type. We have these composite types. We have a field type, which will give you a clue what's coming next. This is how we describe the type. And those paying attention when we were digging into the payload slightly earlier will notice that these match. And we said this was a fingerprint that uniquely identified a type. And the fact that these two hashes are the same, well, that's going to pay off. You've got to figure it in a little bit. So the next thing, what else do we need to describe a composite type? Types have properties. So we have these fields. And if we look at the first one, well, again, we have a list. What is the list? Oh, well, the first thing is the type. This one was an int. It has a name. It may seem that we are digging into some really trivial information, but to re-encode data once we've lost every state, we have to have a complete description of the type. OK, so what is the next step? Well, we know how data is stored, and we know how type information is stored. Well, what's next? Well, we have to marry the two. We have to bring them together in a beautiful ceremony. And we know the list is an envelope. And we know our payloads and schemas are both lists. So we can try and wed the two together. How are we going to do that? Well, we have a fingerprint. So we know that we can look up this type in the schema. Once we find that reference, well, we have a complete description of what comes next. We know that there are a bunch of fields. We know those fields will correspond to the data we encoded in the payload, and we know that the description of those types will let us decode it in a way that makes sense. We can reason about it. And now, OK, fine, great, we've got into the schema. Well, we can use that in the same way at compile time that we can at runtime in Java to build a list of instructions to understand the payload. We've looked inside the blob, and we know how we could go about building something that will understand the payload. Well, let's have a look at a case study. So it exists. This project kicks off. It is in the experimental directory in Corda. You can go and check it out today. It uses CMake. It's a C++ project, so it uses CMake. Obviously, check the README for any library dependencies that may exist. But once you've checked it out, once you've got the build environment set up, well, just change it to that directory and type make, and it will run. And then what am I going to do once I built a binary? Well, then I can run it. And if I put it in a test file, I will get this out. Now, the eagle-eyed among you will notice we're actually cheating a bit. What we said earlier was, well, we can use the schema to create a set of instructions just like we did in Java. But we didn't create any objects. At no point did we do any runtime class parsing. We didn't kick off into, we just printed information to the screen. And I can see what everyone else is thinking. I just sat through 145 slides, and I am disappointed as Picardas. This was the result of 146 slides, a string. But what you've got to think of is from here, we can do anything. The possibilities are genuinely endless. If we understand this, we can build it. Can you imagine building a Swift wallet that actually runs on an iOS device? We could write a native Python or Rust implementation. All it requires is a little bit more work. You can write a full backchain analyzer in C++. Heck, we could even have a native JavaScript RPC client. You wouldn't have to do any translation. Heck, we could go crazy, and we could kick Java out of the picture entirely and rewrite Corda in C. It's worth noting, because I really do quite like my job, we are not going to do this, and this is not policy. So I just want to leave you with answering the question I'm sure you all have, which is, what can I do? Well, you can start your own project. I kicked this off over a long weekend at my parents', and I've been doing this in my spare time because it's fun. Like, we could all wait for R3 to sanction the work. We could all wait for somebody to come along and do it. But heck, this is fun. Start your own project. Don't talk to your family. Write code. You can go into the code. We have a Java inspector. We have a C++ inspector. We can execute this. We have a schema dumper if you want to get more into the way we actually represent information. It's a second project. All of the DevRel people running around here today would lynch me if I didn't point out that we welcome contributions to Corda. I was the former release mistress of Corda, and one of my favorite things in writing the release notes was thanking people for their contributions. Corda, as everyone said this morning, is a community. We love getting other people to help build this ecosystem. Heck, and this is a slightly selfish one, you can contribute to the C++ projects. There's an awful lot of work here, and I would love to make this a reality. But there's an awful lot of work to do, and they don't let me have fun at Arthur anymore. I don't get to write code. So please, heck, contribute. I mean, finally, just have fun. Hopefully most people in this room are software engineers, and I think this is the best job in the world. We get to make things. We get to play with Corda. This is just fun. Anyway, thank you very much.
Any questions for Kat in the audience? I don't think we had any in the app, so.
So you said that one of the things this might form the basis of is some sort of wallet that runs on iOS or something, and there's a few other.
That was very future-looking.
Yeah, I know. I'm waiting for someone else to do that. I'll assign that. This could be one way you could send us a transaction, have it deserialized on a mobile device, and it would be exactly the same. I mean, what are the advantages of doing that versus sending? There's some other ways you've talked about transaction summaries and things like that.
Well, ideally, what I would like is that we would have a completely native implementation that's at both sides. Corda is both an implementation, but it's also a protocol. We have a stable wire format. It doesn't have to be limited to Java. It's just that's what our current implementation is. Some of the limitations of moving something like iOS is, well, you have to be even a Swift or Objective-C. So the ability to do that natively, to take a state that was encoded in a cold node, sent to your iOS device or whatever, and be able to work with that natively to then sign it again and send it back, that's a super powerful thing.
Any more questions in the audience?
Why isn't it being done? That's an interesting, so the question was, why isn't it being done? And the answer is, there are other more important things to do. Building out the Corda ecosystem is super important. Java runs almost everywhere. And you can interact with it RPC via, just bringing a Spring Boot roleplay. This is just something else you could do. It is something that I find interesting as an academic, as a former C++ aficionado. It's just kind of cool. I would heck, go and pester product management. They are lurking around out there. I would love enough pressure on Richard Gendel-Brown right there to be able to go, heck, we are going to write this in C++. But it's not R3's, and it's not in the best interest of Corda to really put many resources into it. We have an ecosystem to build out. We have some cool tools to deliver, and we have all of the promise of that to fulfill. So hopefully it will eventually happen. Native clients in Python and C. But right now we've got more important things to do.
One more. Why did you skip the creates? What would it have taken to
Well, that's next on my list of things to do. And actually, it's something that Mike Hearn was working on earlier. If you dig around in the Corda repo, there is a branch under Mike where he was looking at code synthesis. And fundamentally, it's just a lot of work. You'd have to take a Java object that represented your state. You'd have to build a C++ version of that, so you'd have to basically write a parser at this point or some kind of cross-compiler. We'd have to work out how to fingerprint the Java type system so we could match. And blob inspecting is easy to start with.
Could you feasibly do that such that you could then take a hash of this newly formed object and it would be the same as the hash would have been?
That's the plan. It'll be very difficult, but it's not. I mean, nothing is impossible. Software is wonderfully flexible by just applying a little bit of effort and a little bit of craftsmanship.
Okay. Any more questions? If you do have any more questions, I'm sure you could find Kat around here somewhere. But thank you.
Thank you very much, everyone.